what if there is no other series that we can compare ours to? So for series un, there is no Vn that we could compare it to. To test for convergence or divergence, we would have to rely on comparing a series to itself. Now, one of the early pioneers of this was Jean d'Alembert, a French mathematician who came up with the d'Alembert ratio test. It's a very simple test, and it basically works like this, that un, any particular term in this series, divided by un plus 1, being greater than 1, is an indicator of convergence. It's going to be a series that converges, and the same is true un over un plus 1 being less than 1 is a sign of divergence. So let's have a look at some familiar series, and we can see whether or not it's going to converge and diverge. So if we're quite happy with this one, 1 over half, 1/4, it's an eighth, etc. Is this, or is this not, converging or diverging? So doing this in the limit of n going to infinity, we have un plus 1 equal to L, where L meets the criterion of being greater than 0 for the series of convergence, or L being less than 0 for divergence. Let's have a little look here. So a half divided by a quarter is equal to, what is it, a half divided by a quarter is equal to? It's equal to a half divided by a quarter is equal to 2. And a quarter divided by an eighth is also equal to 2. So therefore, this is greater than 1, this is convergent. What about the harmonic series? Let's have a little look at that. So half plus third plus quarter plus fifth. Half divided by third is 3 over 2. Third divided by quarter is 4 over 3. It's greater, therefore L is greater than, oh my goodness me, that should be a 1 there. L is greater than 1, and so therefore this is convergent. What about 1 plus 2 plus 3 plus 4 plus 5? Let's have a little look at that. 1 divided by 2 is less than 1, and 2 divided by 3 is less than 1, and so all of these are less than 1, therefore this is divergent. So what use is d'Alembert's ratio test in physics? Well, here is a fantastic example that I've just spent 2 hours figuring out, and it works. All right, so the setup is this. Pay attention. We have 2 trains, train A and train B, and they're both moving towards each other, and they see each other, and they decide that they've got to brake. So they both start decelerating. It's 100 meters between them when they first start decelerating, and I've picked values to start with so that they both end up at the same place at the same time with 0 velocity at 75 meters, just here. So this is the point, and I've very specifically chosen values because I want to know that this situation has the distance between these 2 trains converge at a certain value, so that later, when we apply d'Alembert's ratio test, it should demonstrate, it should suggest to us that this is converging. So we're deliberately picking a convergent situation where the distance between these 2 trains converges to 0 in each incremented time interval. So what values did we choose? Well, we had to pick carefully. We chose for this particular train, and we described this train here as A and this train here as B. So with reference to this point here, this train is following s equals ut plus half at squared. So what we found out is to make it get to here, we chose a value of moving forward at 12 meters a second and decelerating at minus 0.96. That takes it from 12, all the way down to 0 at 75 meters. The other train, with reference point to this point here, it starts off going this way at 4 meters a second, and we've chosen a value of 0.32, which will have it stop in 25 meters. Okay, so where is the train at a given time? So what we have with the first train is where it is at a particular time is indicated by where it was plus this function here, which you can see on there. Now, because it's starting at 0, then it just becomes that same thing again. It is just 12t minus 0.48. I've applied the half to the minus 0.96 there, t squared. But the other train is starting relative to this point, which is 100 meters away. So what we're actually saying is that its position, it's the same, it's this, but it's being taken away from the 100. So its position at each particular time, we have to subtract from its starting point, which is 100. So we end up with this expression for the position of train B with respect to time. Wait, this gets better. So what I became interested in is how far the trains were apart from each other. So I took the expression for one train's position at any given time, train B, and I've taken away the position with respect to time of train A, and this produces this expression for the distance between them. But I'm not interested in that as such, because that just peters down to 0 as time gets to about 12.5 seconds, the point chosen for both trains to reach this point here. What I'm interested in instead is these two expressions here, the position of the train. What I considered was this: how far has each train moved each second? What was the change in its position each second? So what I considered was, for train B, I basically thought, well, there's the expression for this time now, but what I need to do to figure out how far it's gone since the last time, I need to subtract what the value of where it was a second ago. So I've basically put in here the same expression as before, but then taken away what that expression would have been one time interval before. And imagine these time intervals are 1 second long. So basically it's 100 minus 4t plus 0.16t squared minus 100 minus 4t minus 1 plus 0.16t minus 1 squared. And so what I've actually done here is I'm taking away this value of position from the value of position in the last time interval. And that is actually producing 0.32t minus 4.16. And you might think, hang about, look what's just happened there. By subtracting where the train is now from where it was at the last time interval, I have independently used calculus. This is basically the first differential of that. And it's actually a proof of calculus within the actual thing. So I've got an expression for how far has this train moved in each time interval. I can do it with the other train, and I get another expression for how far that train has moved in each time interval. Now this is where it gets really, really good. Looking at this expression here, which was the expression for how far these trains were apart, I could now actually compare these two values and consider how, what's the right way to describe this? How far they have moved in each time interval. So if I take y is 12.48, this expression here, so I want to know what this was, and minus how far it's moved in the other time interval, then what I have is an expression that gives me the total amount of change in their position relative to each other in a given time interval. So I know how much they've crept up to each other in each time interval. And it starts out, if we drew this up as a graph, where am I going to go? I'm going to go over here. It starts out that this is obviously a straight line. At about 17, in the first second, they make 17 meters of progress towards each other. And then in the second second, they make slightly less, and slightly less, and slightly less, until we get to this point down here at 12.5 seconds, where they're making no progress towards each other because they have stopped. So, D'Alembert, we did say this was going to be about that. If we consider then this simplifies, I'm sorry, I've gone above, but it simplifies to the expression which tells us about the total amount of difference in distance the two trains are making in each time interval. We get this expression here. And what we can do for each time interval, for t equals 1, we know that the total amount of difference in position that the trains have reached is between them is equal to 15.36. And in the second, how much difference in position have the trains made on each other? Well, it becomes 14.68. And then in the third, we have the difference in position as 12.8. So D'Alembert's ratio test, which was in the limit of n going to infinity, the particular term divided by the next term has got to be equal to L, where if L is greater than 1, it's convergent. If it is less than 1, it is divergent. And so, therefore, what is it for this? Well, if we did 15.36 divided by 14.68, we get 1.04. One more, just to test that it's good. 14.08 divided by 12.8 is equal to 1.1. Therefore, L is greater than 1. It is convergent. Proof of concept.